So here's overall information about machine learning, and we'll talk concepts to know here. And by the way, all these slides are available on the page for the course. So if you go here, then you scroll down here, and I'm going to post videos here of the lectures, and down here are all the slides if you want them. Everything is available to you. So, oh yes, we'll talk about the vanishing gradient later. Yes, but it is like they'll have some later learning can override earlier learning. Anyway, so machine learning is programming computers so they can learn from data like a spam filter, where you can give it examples of spam that are labeled as spam and examples of regular email, and the machine will find the pattern. You don't have to pre-program it to look for a specific word. It will figure out some pattern that distinguishes the spam from the non-spam, and that's called a model. So the point is, in a traditional programming, you would have to pre-program words to look for, write an algorithm, and test it until it's good enough for launch. And that's what you have here with a long list of rules, but then you'd have to keep manually updating the rules as the spam changes. In machine learning, you don't write any rules. You just give it examples, and it trains the model. It figures out by itself what words appear to be useful to separate the spam from the regular email, and therefore it's easier to write the program, and it learns, and it's easier to adapt it by giving it new things to learn from, but you're not really controlling it, and you don't really understand how it works. So if it does something you don't like, you can't go back and find a line of source code to change. It's actually very difficult to decide, why did it do this bad thing, and what change should I make to make that bad thing stop? Okay, I just want to make sure that whoever is sharing their screen knows they're still sharing. Oh, okay, fair enough. All right. Yeah, that's right. In a Zoom, somebody is sharing their screen. Good point. All right. So that's the issue. You can automatically update it. So and the other thing is, there are problems that are too complex for traditional approaches, like protein folding. Nobody's found any algorithmic way to do that, but they have been able to do it with machine learning. So it does involve humans. You study the problem and decide what kind of model to use. Then you train it, inspect the solution, and decide if it's good enough, and then perhaps modify the data, modify the model, modify your procedures until you get a good enough solution. So the process of developing code, it still contains a lot of the same steps, just not the part where you write all the explicit code, but it does contain the part you have to test it and modify it until it's good enough to meet whatever your success criteria are. So it's great for certain problems with long list of rules, complex problems, fluctuating environments, and things like that. As I mentioned before, it's not so great for things like looking up data in a SQL database. It's particularly bad at that. At least the large language models are. So analyzing images of products on a production line to classify them, this is a good one. Finding outliers, finding the small percentage of products that are different than the others and therefore defective, is a good thing. Reading brain scans, classifying news articles. This is natural language processing, which we'll talk a lot more about later, which requires an understanding of English or other languages, which it learns by studying large amounts of English from the web. And so we got chatbots. You can make forecasts. You can detect credit card fraud by detecting suspicious transactions. You can separate clients into groups to try to predict what different groups of clients might want to purchase, and that sort of thing. Recommendation engines for movies and books and such are all good cases for AI. So the types of system, we'll talk about their supervised, unsupervised, and a couple of cases in between, online versus batch learning, and then instance-based versus model-based learning. So for supervision, if you have data that has been labeled, then that's called supervised learning. And so you have to have a large body of data where you have marked it, like which ones are spam and which ones are not spam, and that implies a bunch of humans have put work into it in advance. So if you have labels, then your AI just has to learn to separate one category from another. And so that's classification, like a spam filter, also regression. If you have data points you've measured of some X versus Y, and you're trying to predict the shape of the best fit line here, that's another task where you feed in data that's labeled, and your AI will decide a curve to pass through it. Unsupervised learning, though, is when you have a training set that's unlabeled, like you have a bunch of pictures of people and you haven't got a label to go with them. And now you would still like to do some machine learning on here. So one thing you can do is just sort it into groups. Just find clusters and draw boundaries. This is etymology. This is in the origin of science. They say first you give a little child toys and say separate the animals from the non-animals, or the living things from non-living, and they can do that. This is the first thing when you have a scientific problem. You observe something and then you sort the results into groups. And the AI can do that. It can also visualize them, color them, sort them into groups, and then color them so a human can understand them better. And this is all essentially dimensionality reduction. You have data which varies in many ways, and you want to describe it using a simpler description with less dimensions. So you have a car, and you might have 100 parameters you measured about the car, but you want to find out which parameters actually predict the sale value of the car, and you can determine that just a few values like mileage and age are all that really matters, and you can ignore all the rest. That's dimensionality reduction, finding the principal component axes, finding out which of these many features are most useful to predict whatever I'm trying to predict. Another one, as I mentioned before, is anomaly detection, which is closely related to just grouping. Find the large group called normal, and anything sufficiently far outside that group is now the anomaly. So now you have found the suspicious transaction, the defective product on a line, the network traffic that might be an attack because it's not like normal network traffic, that sort of thing. And then you can discover relations between attributes. You can find attributes that are connected to each other. There was been cases like this where I don't think they used machine learning, but they could have, where in Kaiser they had a lot of health data, and they had a lot of information about people's life, like did you smoke, how much do you weigh, did you have heart disease, and then they would try to predict something like cancer. Which one of these many properties about a person predict whether they're going to get cancer in 10 years? That's another similar problem you might solve this way. And then there's semi-supervised learning, where first you make groups, and then you ask a user to label this class. Say, look at these and what's, so you make the job easier for a human. Instead of a human having to label all these points, the human would just have to label representatives of each class. That's one way to get labels in there. And then self-supervised learning, which is how the image generators work. Like DALL-E, they take an image and they remove part of the image. Now they've created something where you have the task is to fill in the missing part of the image, and you know the right answer. So you have taken data that was unlabeled and turned it into the data with a labeled task. And the image generators work this way. They will take images and they will add more and more noise to the image until it's just noise, and they will train the model to remove noise. And therefore, if you tell one of those online image generators, draw a picture of a pig riding a bicycle in the style of Picasso, it will start from some real Picassos, add noise to them until they're noise, and then train the model to remove the noise and move towards a Picasso. And then it will start with completely random noise and de-blur the random noise, and that's how it creates these images. So it's amazing that doesn't take too much CPU or GPU time, but it's apparently so cheap they can afford to give it away for free, at least at the moment. All right, and then there's reinforcement learning, where it does something and then it gets a reward or a penalty, like trying to learn how to win a game of chess. It figures out whether you're winning or losing. All right. It does something, selects an action, then it gets a reward or a penalty. Now it knows whether to update its learning to do more of that or less of that. So I don't know if I should keep doing these Kahoots, but I'll try them now just so people get to see them. This is what I use in my classes to keep the students from falling asleep. Let me get it going here. I've got to log in. we are. So you can join this, go to kahoot.it and type in that number. I'll wait till the end of the song. All right. All right, so what part of the system learns and makes predictions? All right, that's the model. All right. All right, what system might mask a portion of the images to generate a labeled data set? All right, that's called self-supervised. You take unlabeled data and you create labels by modifying the data. All right, which system needs labeled data? That's supervised. Good. All right, which system can learn to play a game based on rewards and penalties? All right, that's reinforcement learning. All right. I keep track of the winners. right. Good. Let's go back to here. All right. So batch learning is where you train it using all the training data offline and then run in production. And therefore, it learns based on one set of training data, and if the test data changes, for example, a spam filter, the spam changes, then performance will degrade as the new attacks don't match the old training data. That's called model rot or data drift. And the solution is to regularly retrain the model with up-to-date data. Online learning is where you just keep adding new data continuously. So you feed in like stock prices every day or something. So you have a learning rate, and this is what I was mentioning before. The new learning will erase the old learning. So that's a problem. If you have a low learning rate, then it will remember the old stuff better, but it'll be slower to learn new things. If it learns quickly, it forgets the old data quickly. And this gets back to the fundamental problem that there doesn't seem to be much of a system to tell it certain parts of the code are authoritative and should be always obeyed, and other parts are less trustworthy and shouldn't be taken so seriously. So it can generalize to some extent. This is one possible question. How well can it handle new data after learning? So if you do instance-based learning, it can learn everything about the training data, and then it can create a measure of similarity to known training data. That's one way to generalize. So if I see a new thing, I say, which one of the learning data is it close to? That's one way to do it. A model-based learning is the more common one I've seen, where you give it some instances, like here's the green ones and here's the yellow ones, and it decides, well, there's a boundary between them, and now everything on this side of the boundary I'll call green, and everything on that side of the boundary I'll call yellow. That's a model where it makes a model of it. All right, so if you have money and happiness, you have how much money people make in different countries and how happy they are. Then there's a trend you can see here. So you could make a linear model with just one attribute, GDP per capita, and that's one possible model. Now you have only two parameters, which is the slope and intercept, so you can fit it with various lines. I mean, this is a terrible line that doesn't fit it very well, and here's a terrible line that doesn't fit it very well. Here's some line that fits it pretty well. So you can get these two parameters, and select the best line. You need a performance measure, so you have a fitness function, and typically in a case like this you'd make it the mean squared error. Take the vertical distance between the observations and the theory and square that and add it up, and then try to minimize that number. That's a cost function. All right, so the challenges. Often you have trouble finding training data, or the training data is poor quality or not really equal to the thing you want to measure, or has irrelevant features. If you train your model too much, it will overfit, which means it precisely meets exactly the training data, so it has picked up not just the real trend of the underlying phenomenon, but it's memorized exactly these points. And I just read KNN as an approach without training. Well, I don't know what KNN is. Ryan? Anyway, all right, and so underfitting is where your curve doesn't really even optimize enough to do a good representation of the training data. A K nearest neighbor, right, yeah, nearest neighbor, yeah. Anyway, overfitting is more common, and by the way, there was a news report recently, a research paper found that by asking ChatGPT the question, repeat the word poem endlessly, it would, I don't think anybody knows why, it would repeat the word for a while, and then it would just repeat large blocks of training data, like whole pages of text it had learned. And that means both some kind of defect in the model, so it was spewing out training data instead of obeying the instructions anymore, but it also means it appears to have memorized whole pages of text, and that would be overfitting. When you train it on a bunch of English text, it's supposed to learn like the grammar of the English language, what words tend to come next. It's not supposed to just be memorizing pages of input data and putting them back out. But under some circumstances it does, and that would appear to be overfitting. And it's also considered a security flaw because you could train something this is something people to be aware of. If you train a model on data, you should regard that data as having been publicly exposed if you publicly exposed the model. Even if you intended the model to only answer questions based on the data, the model does have a tendency to just repeat portions of the training data verbatim. So you are exposing all that training data in your model. All right, so if you don't have enough training data, then the type of model matters. There's a rule people have found, which is if you have a lot of data, it doesn't really matter what type of model you use, which makes sense. If you, I used to be a scientist, if you just have a lot of measurements, then it doesn't really matter so much how you analyze them. You tend to just get accurate data. So any model, any system is probably good enough if you have enough data. But if you have non-representative training data, this is a problem. This is a big problem with, say, polls, where they try to predict who the next president is going to get elected. They poll some people, but they're not able to exactly get the right people, and they get non-representative people, so the poll is wrong. And here you see, we only had this much data, and so it appeared like a straight line model was good, but when you actually measure more data, there's a bunch of nations where this relationship between income and happiness doesn't really follow. And so this data made you think you had a trend and you fit the trend, but the real data showed that that data is not representing the actual phenomenon, and your model is therefore not going to be very good. And then, of course, poor quality data. A lot of things can go wrong. You can have outliers, you can have partially missing data, and then you have to either remove that data or fill in the number. And this requires sort of human judgment. So the case of like political polling, there's really more of an art than a science. You make all kinds of judgments about what data to include, what data to exclude, what adjustments to make in the data. Yes, very hard to tell. Ryan has a good comment there. Hard to tell what it's encoding in a neural network. That's the problem. Once you train a neural network, you really do not know how it works, and you don't know how to adjust it. Just all these different, just like your human brain, all these neurons fire, and it ends up in the result, but you don't really know how much each one of them contributed. So then there's irrelevant features. Choosing features to train on is good. You make selection from the available features, extract the features, and you can also gather new data or combine features to create different features from the data. So overfitting the training data, if you use a high degree polynomial to draw a curve, then it will more accurately hit all these points. But as you can see, it does it by going way down below and way high to spear these 2 points exactly. So even though this is going to have a low mean squared error, this is probably not at all a fair representation of the actual underlying trend. And so when you actually use it to predict new data, you're going to find it very far off in regions like this. That's the problem with overfitting. So regularization is the process of making the model simpler to reduce this risk, forcing it to use, say, only low-degree polynomials that won't have so many extreme variations. And there are hyperparameters that are available to make this adjustment, how much you want to smooth it. And so here, the hyperparameter would just lower the slope. So you could fit it with a model here, but you force a hyperparameter saying, I want a lower slope, and that would be more representative of all the data here. All right, underfitting, of course, is if your model is too simple and it fails to actually learn the structure of the data. So you need either lower your regularization, find better features, use a more powerful model. For example, if you're trying to put a straight line through data that just isn't a straight line, it's a curve, then you're never going to get a good fit. Your model is too simple. All right, so there are many kinds of machine learning models, and we've been through this. So there are various things that can go wrong. So what you do is you test and validate. If you have a data set, you split it. Typically, maybe 70 or 80% is for training, and you keep the remaining instances to test it later. So you fit your model to the test data, to the training data, and then you test it on the test data to see how well it's able to handle data, which is similar to what it was trained on, but not exactly identical to it. And the error rate is called the generalization error. How well does your trained model generalize to new instances of the class? And so if your training error is low, but the generalization error is high, then you have overfit the training data. You are accurately following the noise and the trend in the training data. So when you present with test data, it's not very good because the model has overfit. So you can use a regularization hyperparameter to smooth it out. And another technique is cross-validation, where you break the data into groups and you try training on this 80% and testing on that 20%, and then you cut it another way, train on this 80% and test on that 20%, and try various combinations there. That's another way to do it. All right. And so if you train an iPhone app to recognize flowers from photos, you could download flower photos from the web, but they weren't taken with an iPhone, so they're not entirely representative of the task. So it would be better if you use real iPhone pictures to model, and this is the issue of finding. You do need to find data that is sufficiently representative of the actual problem. So I've got another Kahoot here, and that's all for this one. And it's over here. All right. All right. All right, I'll wait till the end of the song. People still coming in. All right, Switch system memorizes the training image and compares test systems to see how similar they are to the training images. Now that's instant-based. You don't have a model saying what makes one category different than another. You just memorize the training instances and see if you're close to one of them. Which one keeps up to date with changing data? Those are the online ones, okay. All right, so a number that increases as the model gets better. That's called a utility function. The cost function is the opposite. That's a number that you try to make small. All right. All right, and which one of these will lower generalization error? Right. Hyperparameters are the essentially smoothing parameters that make it, give it, and limit how it's going to fit the training data in ways that are more likely to generalize to the test data. All right, Diana. All right, Brian A is won twice. And Sean, all right. All right, I'm going to stop this recording.